Now, obviously, we need to have a circle to talk about circle theorem. Okay, so we're looking at this circle. Now, we're saying that there are some key parts of a circle that we need to understand. This part here, we call it the center of the circle. So here refers to the center of the circle. A little bit here. Now, if this is the center of the circle, if we connect from one point to the center to touch the circumference or this arc here of the circle, we would refer to that piece as a radius. Okay, so from here to here, we're talking about a radius. Now this here is a radius, but if we draw a line straight across and it passes through the center and goes to another point, we call that the diameter. Diameter. So the red part is the diameter, and this part here is the radius. Okay. Diameter. And this part here is the radius. Okay, so we got a different situation now. These are the key things we need to understand when doing circle theorem. And these here are separate entities. So if you're looking at this circle here in this part, we have a radius and a diameter. Now here, what we're looking at is another circle. We're going to have a center again. And what we're saying here now is that we need another line. So we'll draw some lines here now. However, notice we'll let this line go. We'll try to let this line pass over here. But if you look at it, it's not passing to the center. It's not passing to the center. Likewise, if I draw this one here, this is not passing to the center either. Okay, so when we have stuff like this, what we call these are cards. We call these cards. Okay, we call these cards. All right. All right, so if we have those and we have these as cards, we need to understand that this and this, these are not the same. They're not equal. They're different things altogether. This here, cards, cards, cards. This here, diameter, radius. Two different situations we're talking about here. Both of these pass to the center. This does not pass to the center. Okay, so that's the basics of these two circles here. Next thing we need to look at now. Triangles. Triangles. So we got major triangles that we talk about. These triangles that we talk about, we have one that has the same sizes and same angles. So for instance, here would be 60. Here, 60. Here, 60 as well. So let's say this was the length 10. This was 10. This here would also be 10. This here would also be 10. So we call these triangles equilateral triangles. And the name is kind of obvious. We say equilateral because they are the same size throughout. Everything here is the same size. Okay, so angles the same, length the same. That's why we call it equilateral. Now, what about if we have a situation where we have two sides the same? Two sides the same. Two sides the same. The angle here would be the same. So for instance, if this was 70, here would be 70. And here would be 40. All right, another combination could be 80, 80, and 20, you know, 75, 75, and what's not. Two of these are the same. No, two of these angles are the same. So are the lengths. So this length here would be the same as this. How we usually denote it is like putting a dash to show that it's equal. So these two lines equal to this two dashes here as well. Now with this one, all of them would have had the same line here. Okay, so this, all three equal. This here, we got two here that are equal to each other. All right. Now the next one now, we call this isosceles. All right, so this is a situation where they're different lengths. They're not the same length. Okay, they're not the same length. So all are different lengths. I could indicate this by doing this. So as you can see, different lengths. You got this here has one on it. This here has two. This here has three. So they're not the same length. This is just indicating to me that it's not the same length. So if you look at this now too, I got two dashes here, two dashes here. I mean, two of these are the same. This here got one dash, one dash, one dash. So somebody might be asking, does it matter the number of dashes? Well, not necessarily. It just matter that they're matching. So for instance, if I had these two, I need these to show that these here are equal. Okay, once I have the same balance, I know that they are equal. So that's a key thing to understand about triangles in themselves. Next thing to understand about triangles, so I could write down this, isosceles, and then here would be a scalene. Okay, so isosceles and scalene. So the next thing would be these triangles, no matter what the sizes are, they all add up to 180 degrees. Okay, 180 degrees would be the sum of the internal angles. So we're talking about the internal angles of a triangle. So these internal angles add up to 180 degrees. So it doesn't matter what triangle we have, it's going to equal to 80 degrees. So let's look at a triangle now. We have this triangle here. If I put two dashes here, I'm saying that two of these lines are equal to each other. If I have these now, I could say, let's put here 80. And I want you to find X and Y. All right. So I want somebody to tell me or text in the chat what they think Y is equal to. What they think Y is equal to. What do you think Y is equal to? What are the degrees of Y? Nice. So this here, 80 degrees. Excellent. Because two of these here would be the same. This here and this is 80. We know that because these lines are the same. Now the next thing is, how would you know what x is? What would be the value of x? Nice, 20, excellent. So the way you would have figured that out is because you know that a triangle adds up to 180 degrees. Okay, so as we were saying, we got these three main triangles. So equilateral, all three sides are the same. So if this one was 60, we know all are 60. Now, if this here now, we in this situation now, this here is an isosceles. Why? Because two are these the same size and the other one is a different size. So we want to know that, okay, if we add these two that are the same, that means the angles here got to be the same, then we could work out the other one. A scalene, all lengths different, all angles different. Now we're looking at this triangle here now, and we realize that, okay, these two lines indicate that these are the same length. So if these are the same length, that means the angle here, if it's 80, that means this angle here must also be 80. Okay? And if this is 80, this is 80, then right here would be 20. Why? Because sum of the internal angles of a triangle equal to 180. So we know that 80 plus 80 is 160. This here is 20. Okay, now notice, I want you to bear this in mind. We're looking back at something we looked at first before we started, right? We said that a center of a circle, we have a center of the circle. If a line touches any point along the circle and goes to the center, that is a radius. And the diameter, once it passes through the center, we call that equal as well too. This here is the diameter, passes straight through. And if you look at here now, the chord would be if we're in a situation where we don't pass the center. If we don't go through the center, we call that line that touches one end to the next end, and a straight line that touches one end to the next, a chord. Okay? Now, this brings an important situation here now. So how does this link to circle theorem? Now, if we have a circle, and right here, let's say this is the center of the circle. And now I have a line passing from here to one end. Okay. And then I have a next one passing from here, center again to another end. Without saying it, I know that these two lines are the same length. Okay? Just say I was to connect this as a arrow now. Not an arrow, as a triangle. I know that these are the same length. How do I know that? Well, just look at it. Let's change the color of these so we could stand out. We want a triangle to stand out. So remember now that these here are the radii. Two of them together are the radii. So we got one radius, two radii, right? So if you look here, the length of this, if this was 10 centimeters, that means from here to here has to be 10 centimeters as well. Why? Because it's the same radii, right? They have the same length. Boom, boom. So I know these here are the same length. Therefore, if I have an angle that's inside here, and I told you the angle here was 40, automatically you already know what the angle over here is. Why? Notice it's passing through the center. It has to pass through the center. Okay, so therefore this does not count. If I had this here, circle here, and I had a triangle going like this and come into this, I cannot say that angle here equal. I can't say that these two here are equal. I don't know for sure. Who knows? Maybe they are. I just don't know. You could only know for sure if it's coming from the center. It has to come from the center. So that means if this is 40, this here also has to be 40. And if these two are 40, I know that this angle, when I add all of these up, supposed to add up to 180. So 40 plus 40 is 80. So to get 180, I just need 100. So I know this here, this little piece here would be 100. This here is 40. This here is 40. Now, that's if we are given this angle. What if we had a situation where we were given the other angle? So for instance, let's look at this. So we have this. We have this here. Let's say we did not know that this was 40. Okay, but we're trying to figure it out. So we're using the same question, but we're trying to figure out these angles here now. Okay, so I'm not going to add any names to the angles as yet. I'm just going to talk about how to get this angle now. So if you're looking at this now, this is 100. Now, when I looking at this, I realize, oh, look, this is a radius. This line here is also a radius. So that means two of these have to be the same length. So if two of these are the same length, that means the angles here and the angle here must be equal. So how many more do I need to make 180? I need 80 more, but because I know that these are equal, that means that two of these have to split between that 80. So I know inside those angles going to be 80 divided by 2, which is 40. So here's 40, and here is 40. All right, so that's one situation. So that's how we could think of triangles that come from the center of the circle and form. We know that these angles are going to be the same. But notice what it formed on, what those angles are sitting on. A chord. So this here is a chord. How do I know that it's a chord? It's a line passing from one end to the next, but not passing through the center, right? So if you look here, we had chords here. Okay, so just to make light of what we just had, it's like we draw this here, that's a radius. We draw next radius, and it's sitting on this chord. So if this here was 110, that means these two here now need to add up together to be 180. If you look at that, that's going to be 180, take away 110. That's going to give us 70 degrees. So now 70 degrees, if I was to divide that by 2, that would equal to 35 degrees. This would be 35. This here would be 35 as well. Okay, so that's how you have to look at that, right? Now, let's look at another scenario now. So this is one scenario of a triangle. Most of the circle theorem is made out of triangle theories, you know, and quadrilateral theories and so forth. So we're going to look at the triangle theories first, so you can have a better idea as to what's going on. So we just understood what it is to take the radius, put a chord on it, make a triangle, and figure out those angles. So the next thing we're going to look at now is what happens when we have a diameter. So this diameter now is going to come from one end to the next. Okay, so now this here is the diameter we're looking at, and we want to have some angles falling on that. So let's put these angles to fall from here on this side of the circle. So kind of like we draw Pokemon bar. All right. So if you look at that, whenever we have a situation like that, so we have an angle here. Whenever you see a situation like this, where the angle sits on the diameter, but this is a key thing. This needs to touch this. It has to touch. It has to touch the circumference. Has to. No if, but, or maybe. It has to touch that in order to be considered what we're going to talk about now. So if I had it the same thing, instead of doing that, it was actually over here, like say for instance, and we had these angles going differently. So for instance, you're saying that instead of going there, the triangle went in something like this. This cannot count as, you know, what we're going to discuss now. We don't know if these are equal, so we can't say anything about that. All right. But as I was saying, when we have these angles that sit on this, on a diameter, we know that the angle in here is supposed to be 90 degrees. And it doesn't matter where it falls. Once it sits on this diameter, it's considered to be 90 degrees. That's just the theory of it. All right, so that here is also, if you see it like this, so you put it in words, so the exterior angle, okay, this is for something else, add it here. So an angle subtended by the diameter is equal to 90 degrees. So when we talk about subtending, that means it just close the angle. What do I mean by close the angle? Say this is the angle here. Fancy word to subtend means like if I was to close this angle. So if I was to put like, you know, a tree here, say this was a tree, what I would say to somebody is, yeah, this tree subtends this angle. Okay? Or if I put a red line, I could say, oh, this red line subtends this angle. Okay? Now, if you look at this, what subtends or closes this angle? This red line here, which is what? The diameter. So an angle subtended by the diameter is equal to 90 degrees, and it must touch this here. It must touch the perimeter circumference of the circle, the arc outside. It must touch that as well. All right. So if I was to extend this and put something else here again, for instance, if I had to draw this blue line here now, and let's draw it low here. I want you guys to realize that it doesn't matter how high it is or how low it is. Once this here is the case, we know that they subtend the diameter. So if you look at that, the diameter closes this. So guess what? That means that here is also 90. Okay? Here is also 90. Okay? And what this shows us something else as well. This shows us that it doesn't matter how angles sit down on each other. Once these angles sitting on the same line, on the same diameter, same chord, they're gonna be the same. Okay, so let's tie this up again on another side so you could see it, then I'll explain what I just talked about just now. So for instance, even if I draw it upside down here now, let's make that a different color so our diameter could be distinct. So even if we do that, apologies for this little extra piece here. So if we put that there, this here is also 90. Even though it's upside down, it's still equal to 90. We could put like 100 different lines here, but once they're there, they equal to 90. All right, so that here is 90 degrees. 90 degrees. So if I connect this as well, this also is 90 degrees. I connect here to here, this here is also 90 degrees. So it doesn't matter how many times I connect it. Once it's sitting on that diameter and touching over here, we know that it's equal to 90 degrees. Now, what I want you to realize now is if this is 90 degrees, here we know how much this is. This here is 180. Okay? So I want you to bear that in mind. If this is 90, we know that this here is 180 because it's a straight line. All right, so anything that sits, any angle that's subtended by the diameter is 90 degrees. And we also learned that any angle that sits on the same diameter or the same chord would be the same. Okay, so let's look at that now. We look at that same one that I just described now. So let's say we have this circle here now. We say that the center is here, typically called O. All right. So now we're going to have a little few situations here now. So let's say we had this line going across here. This here is our chord. This here is our chord. And let's say we had an angle that was sitting on this chord going like this. It goes here. Comes here. I'll draw a separate one now. Now this one we want it to be a different color. So if you look at this now, say this one goes here. All right. And then it comes from here down to this. Let's talk about this for a little bit now. Now, if you look at this, we have two different situations here. But what's common between the two? They both sit on this blue card. Okay, so what I could say now is that if I had an angle and said that this angle here was 60 degrees, that would mean that this angle here is also 60 degrees. Okay? How do I know that this is 60 degrees? Well, they sit on the same card. They sit on the same card. And they're in the same sector. Okay, not only are they sitting on the same card, but they are in the same sector. So what's a sector now? So you have a circle. So you have a circle. And then you try to cut it in half, or however you cut it. So let's say from the center of the circle, you cut it. The same segments are. So if you say you cut something here, and so you have a center here, and you cut across with a card. Okay, this part is like a major segment, and then this next part here is a minor segment. Okay, so we are saying that both of these have to be in the same segment or the same portion of the circle. So that's just a fancy way of saying that they have to be in the same portion of the circle. Okay, so if you look at that, this here is like a little piece, like you cut the pizza bad, and then that rest part of the pizza, it's still on that same side. So these angles would be the same. Likewise, if I also did this for another triangle, let's use this. If I use another triangle here, this here, once it passed through this, once it's touching that, this angle would also be 60 as well. Okay, so this here is 60 degrees. So this is 60, this is 60, this is 60 as well. Okay, this is 60, this is 60, this is 60 as well. If you notice how this almost passed through the center, almost gave us a 90 degrees. If that did pass through the center properly, we would have known that here is 90. And then we would have known what this here is, obviously 30, and so forth. Okay, so this here is that theory. Once you have angles sitting in the same sector and they sitting on the same card, they would equal the same angle. The angles would definitely be the same. All right. So we could put in words and say any angles in the same segment and sitting on the same card are equal. Okay, so that's the next theory there. However, I want you to understand that this is not always given. So you see how that is? If you didn't have this and they had a, you had to try to figure out how the angles were, remember, even though there's no line here, you're sitting on the same sector, on the same card, sorry. Okay? It's just that it's not there. So you could, make your own card to prove the point. Okay? You could put your own card to help you understand what's happening there. Okay? So for instance, it could look like something like this. If you look at this here, all these angles are the same. It's sitting on the same card. Is a card there? No, there's not a card there, but we could draw the line and realize that, hey, look, it's the same thing. Okay? So this here is a card that is sitting on. All three of them sit on the same card here. So that means that when we actually try to, work that out, if this was 10, that means this got to be 10, and this has to be 10 as well. All three of them sitting on the same card. Okay, so that's the rules that we just learned so far. So we have isosceles triangle. Once we have this here, we know that's the isosceles triangle situation. We know what this here is. Once it's sitting on the diameter is 90 degrees. All right. And then the next one we have here is once we have all the angles sitting on the same card, we know that they are the same angles. All right. So what I'll do now, I'll put a question together now with all of these theories so far together. So we're gonna have this here with this isosceles triangle. We're gonna have this here with a subtended, and we're gonna have this here in different forms, and you guys are gonna try to come and figure out what the angles are. Okay, so do this one first. So say we have a circle here. And typically when you get these questions, they usually give you, letter names and you have to work them out. But before we get into letter names, I just want you to understand what's happening here with these triangles. All right. So let's say we have this here. Then we had, I'll keep it color coded for now so you could see what we're looking at. Okay, so we have that. Okay. So this. Now let's put this line here. All right. Okay, so let's give it some letter names now. So let's call this A. Let's call here B. You're going to call the center O. You're going to call this point C. Let's call here D. Now, when we're talking about angle names, if I said angle A, B, and C, what I'm saying is that I'm looking for the angle at B. Okay? So I have to give you one of these angles. So the angle that I would give you is this one. So let's say this here was 70 degrees. So I want you to find angle A, D, C. So when I say ADC, I'm talking about the red one, A to D to C. So that means you're trying to find this angle here. All right. Then the next angle I want you to find is A, C, D. Another angle I want you to find is, let me tell you what this one is. This one here is 140, which is another rule. Just showing you quickly. This angle here will be double this. I'll explain that after. That's the next rule we can look at. So I want you to figure out ACD, ADC, O, A, C, A, C, O. I want you to figure that out as well. What else can we have? Yeah, let's look at those for now. See what you come up with. Also, let's try OCD as well. OCD. Yeah, OCD. All right, so let's see what you guys come up with for this. Now, this here is where you got to try to get your mind to see everything separately. Okay, so this is a part here where it becomes challenging. How to decode everything that you've been doing, how to decode it. So your mind got to be able to try and break down each piece as a separate question. And not only that, we need to understand how to see this if it was sideways as well too. What if this was rotated the other way around? Okay, so these are things we need to consider. All right, so let's look at this now. So I'm gonna highlight with color now the things that are helping me to see ADC. So I'm looking at ADC. When I'm looking at this is what's going through my head. It's like, okay, I have this. Like, what in the wall I could use to help me figure out this triangle here? Okay. So what about this? This triangle is sitting on a card. So I know, okay, that's good. What kind of card is this? Well, hmm, it's sitting on a other angle sitting on there. So that means that they got to be the same. So that's what I'm looking at when I'm looking at this. So I'll draw it so you can see what I'm talking about. So I'm looking at this here. So this angle here, as well as this one, the green one, both of them are sitting on this AC. So essentially, it's one of these. Okay, so that means these here would be the same. So I know from that this here is 70, so that means right here has to be 70 as well. Okay, there's another rule that could tell us that that's supposed to be 70 as well, which we'd look at after this. Now, the next thing we need to know, so the reason we would have for that is because when two angles are sitting on the same card in the same segment, which is this here, they are equal. So this is why you would write for your reasoning, why you selected 70. It's not about necessarily calculations, it's just about knowing the theory. All right, so yes, I'm not sitting down here trying to measure this angle to prove that it's 70. I just know based on the theorems that that is the way it is. Okay, so AC to D now. I'm trying to understand what's happening with AC and D. Now, the angle I'm looking at, where is it located? Well, this angle seems to sit on something. It's sitting on what? The diameter. So if you look at that, it's sitting on the diameter. So what does that mean? Remember this rule here? Once it's sitting on the diameter, are subtended by the diameter, it is equal to 90 degrees. So that means that ACD has to be 90 degrees. Okay? It has to be 90 degrees because it's sitting on the diameter. All right? Now the next thing is OAC. OAC. I forget to erase those lines. So we're looking now at OAC. Now OAC seems to remind us of a good old friend. Who's that friend? OAC. Now if you look at this, from here to here is a radius, and from O to C is also the radius. So that means here and here must be equal. They have to be the same length. So the next thing now is if I go over here, remember when we was looking at this, we realized that once we have this angle here, we know that if we split these in two, they equal. Why? Because they come from the same section here, the same radii. This two radii together, they both form, isosceles triangle once they're sitting on this card. So same thing over here. These two radii sitting on the same card. So then we have a situation where we have a triangle here. That's an isosceles triangle. Okay, so that means if this here is 140, angles in here need to add up to 40. How do I know that? 140 plus 40 is 180. Where I get that from? We know that the sum of the internal angles of a triangle have to add up to 180. So if they have to add up to 180, that must mean that 140 plus this must be 180. And since two of these angles are equal, they have to split the other 40 in half. So here is 20, and here is also 20. Okay? So we know that OAC is 20, and we know that ACO is also 20. Okay? That's also 20. Now, OCD. Now this is a new angle now, OCD. You're trying to figure out what OCD is. So from right here, however, we learned something earlier about this triangle. Remember, we said that ADC, that triangle, if you're looking at A to C to D, the angle by C is 90 degrees. Why? It is an angle that sits on the diameter. It's subtended by the diameter. So if this whole thing is 90, that means that if this is 20, both of them together must add up to 90. So that means that here must be 70 degrees. Okay, so in here must be 70 degrees. Okay, so the issue here now is just trying to see, when they separate. Now, for me, when I'm looking at, these situations here, what I try to look for is anything that makes me reminded of a bat. So if you think of a bat, like got this kind of look almost, it got that kind of zigzaggish look going on here. That was a bad drawing, but if you look at this here, for instance, it has that kind of like bat effect, or bow tie, whatever maybe a bow tie is a better example. So what we're saying is once we have that bow tie effect in a circle, so we're just doing that bow tie, look bad, but once we have that bow tie, we're saying that the angle here and the angle here would be the same. All right. So let's try to draw that circle again. If we had this circle here, and we say we had this bow tie, the bow tie going like this, we know that they're sitting here. Both of these angles sitting on the same card. So that means this angle and this bow tie must be the same. So if this is 70, here must also be 70. I cannot assume this is sitting in the center. We don't know. The center could be here. Who knows? We can't assume that. But it doesn't matter because it's sitting on this card. Now, if you look at it upside down now, see this card up here now? Based on that card, in here, this angle here has to be the same as this angle here. Okay, so let's say if this was 60, here would be 60. So all that is that if you look at this picture here, let's try to rotate it. Because remember, we got to see this from different perspectives. Is it going to rotate? No, it's not. It doesn't want to rotate. But if we could get it to rotate, we would expect that this here would be on the other side of that. Let's see if we could get it rotated. Or rotated on something else. Right, so if we have it like this, as you can see, it's the same principle, but it's just upside down. It's the same principle. So you see how the angles here are equal once they're sitting on the same card? Same thing here. The card that they're sitting from or hanging from is up here, which is the same thing as here. So these angles here would be the same. Likewise with this. If I was to say this here like that, remember you could see a bow tie on that. Look at that. This angle here, and then this angle inside here. All right. So these here would be the same because it's sitting on this. So it's just something you gotta like kind of keep looking at to be able to see what's going on. All right. So that's these rules here. So we have a next rule now. A next rule, and then we'll do something like this again, so you could keep connecting the dots and seeing how you have things separately. So with this one here now, we have a next one here, one that you guys like to call Patrick from SpongeBob. So let's look at the Patrick situation. So if you look at this, from here to here, these two angles are sitting on the same card. However, the difference between this and what we were looking at earlier is that these in the same segment, but if you look here, this one does not continue all the way to the end. So in other words, I'm basically saying that this angle does not go all the way up here. It does not go all the way up here, like this. All right, it does not do all of that. It just stays here. Now, in a situation like this, the rule is that whatever is here, this one is twice the size of that. So for instance, if this here was 40 degrees, here would be 80 degrees. Okay, so if here's 40, here's 80, where does that come from? If you look at it, the same triangle that we were looking at over here, it's saying it comes from this. If you look at this here now, we said that once it's sitting on a diameter, it's 90 degrees. But if you look at it, if this is a 100, if this is a straight line, this here could be 180. So this is half of that. This is 90, this is 180. 90 plus 90, 180. Now imagine this diameter, pretend this is legs. All right, so just legs now, but then the legs slide down, this leg slide down, this leg slide down, and it look like this. Okay, so now the angle gets smaller down here. So instead of being straight across, the legs just come down. Just pull the legs down. So if this is 40, this is going to turn to 80. Okay, now the next variation of that would be same situation. So this is like somebody doing a split. So imagine this line here as a leg. That's like somebody doing a split. So if you got a stick man here, this is the hands. No, this looks bad, but just for illustration purposes. This is a man with a split. Okay? Now with this one here, this situation here, it's like the man is standing up. Okay, so the man is standing up this way. He got a big head. So you see now, standing up. So the legs going down this way, and these ones here straight like this. Okay? So we're saying that whatever this angle is here, which is this, is the same as up here. Now with this one here now, when we have this here now, this is like it being straight. Now the next scenario for this situation here would be like this. So let's say we have that there. We have our center. So the lines now going like this. So the guy a little happy now. Feel excited. So he trying to see how high he could jump. Okay. Hopefully these illustrations give you an idea of what's happening. So now, in a situation like this, if this angle here is 200 degrees, that means here could be half of that. 'Cause remember, this is double. Look at this is 80, this is gonna be half, 40. This is 180, this is half, 90. If this is 200, this is gonna be half, which is 100. So our friend now, what he just did, he was excited, so he jumped in the air trying to get a fancy shot, seeing if he could touch, make his hands touch his legs. All right. So he jumped up in the air. Well, 4 fingers. He jumped in the air and he trying to like touch his foot. Okay. So this is what happened here now. So this is 200 now. And this here is 100 degrees. So that's the next rule there. Now, if we look at this diagram that we had here, you would kind of see the same rule applying here. So for instance, you see how this here is? This here is the Patrick situation that we're looking at. So these here, the radii, represent the legs. All right, so if this is 70, we know that right here is 140. But notice, this is a special situation of it. This is like he on a lean. Okay, so even though you can't see the piece of the leg, this whole thing here sitting on the same card. So here is 70. So inside here is 140. Okay, so if you look at that, that's what happened in this situation. So that is the next rule for triangles, right? So I'll show you guys now a question that employs some of these theories that we have here. But I'll give you the explanation for this, right? So for this now, when we're talking about this, we're saying that the angle that is subtended, let's make this bigger for us to see. The angle subtended by an arc at the center of the circle is twice the angle subtended by the same arc at the circumference. You could also put on your own words, obviously, but this is a quote-unquote theory itself. But if I had to say that, I would just say this angle here, the angle subtended by this card here, touching the circumference, with angle from the center that subtends the same card. This one will be twice the size as this one here. Okay? Whatever you put in, you could refer to it specifically because when you have letters, you could say, well, AOC is expected to be twice ABC because X, Y, Z, whatever the case is. So this here is the theory here. So what we'll do now is try to put them together now. So we have a situation where we probably have to answer all of these, and you guys try to figure out, the part. But the key thing is to be able to look at it and see it in different phases, different pieces. Okay, so these are some of the theories we look at. We got other theories, obviously. These are the main ones for now. So let me give you a question to try now. So let's say we have a circle. This is our circle here. We have our center O. Now let's say we have a diameter that's passing through from here to here. What we'll do is we call here A, call here C. So let's add a next line again now. Now let's keep all of them the same color this time. So we have this here now. The next thing we want to look at is this coming right here. We have a next one coming here. Next one coming there. Okay, so we got that. Let's see what else we could have. Call this next one over here. So call here B O B, and the angle I'll give you guys is gonna be this one right here. I'm gonna say this is 65. So what I want you to find now is angle DAC. That's the first one. I want you to find ADC. Let's also find DOC OCD. All right, so let's look at this now. So DAC. So I'm trying to figure out where DAC is. So if you look at DAC, DAC is sitting on what? It's sitting on a card. So I need to see if there are any other angles sitting on that same card. Maybe that might be an option. So I'm looking at that and I realize that, hey, watch, DBC is sitting on the same card. So that's 65. So that means here must be 65 as well. Now notice this. This has a back of the bow tie we're talking about. You see that? That there's a bow tie. So I know whatever angle this is, this would be the same one. All right? So that's what you have to be looking at when you're doing these stuff. Now, next one. So we know that 65, that's established. So two angles, any angles sitting on the same card in the same segment are equal. Next one, ADC. ADC. So what is that angle sitting on? The diameter. So it's sitting on the diameter. So if you look at that, here's where it's sitting. So that means the angle here must be 90 degrees. Must be 90 degrees. So that means here should be 90 degrees. Next one, DOC. DOC. So DOC. So how can we figure out this one? Now, if you look at that, this one has many different variations. If you look at that, this here is 65. So that has to be double with this, which is 130. You could also look at it from this point of view here. This is 65. So we have that Patrick looking thing. This guy just standing up here. This is what we're seeing here. Okay? So he's not standing up like this. He's not flat. But look at that. So then we know that here is 130. Next thing. This little piece in here. What is this? So we could find out ODC or OCD. Now, I want to show you ODC first. Let's just do ODC. So we know that these three angles here are supposed to add up to 180. So this, three of these supposed to add up to 180. So if three of these have to add up to 180, that means that I know what's going on here. We got radii, two radii coming from the center. So that means these two angles got to be the same. So if this is 130, the remaining is 50. So if I split 50 in two, this is 25, and this is 25. Okay? So I know that this angle here is supposed to be 25. We know that here OCD is 25 as well. However, I want to show you something else with OCD. So if you look at OCD, we figured out that this is 65, but we know that this overall angle here is what? 90. So if this overall angle is 90, if I was to separate this as a different triangle and put it here, here is 65, here is 90. Remember, the internal angles of a triangle must add up to 180. So all of these have to add up to 180. So 90 plus 65 is 155. So 180 take away 155 would give you 25 degrees. So all these here add up to 180. So you see now there's a different way of doing it. So in certain situations, you realize that, there are different ways to work out the answers. So always be mindful of that when you're doing these questions. Always be mindful of that. All right, so I'll give you guys a little easy one to try for homework. Then tomorrow again, we look at this God sphere life. Because I think once you catch the concepts here, and then you try to apply the new ones together, it will give you enough exposure to understand circle theorem a lot more. Okay, so this comes with exposure. Exposure, just looking at these things over and over and over again, you start to pick up the patterns and figure out what to do. So I'll give you two to try, and then we look at some other theories tomorrow, God's willing. All right, so look at them here. So this is the first one, and this here is the second one. It's a similar concept. Just want you guys to take a screenshot of this and try to work on two of them. Try to work on two of them. All right, so until you guys practice this, we'll catch up another time.